Lissa Productions.
So today we're going to be talking about IV curves and equivalent circuits. We'll start with an IV curve, which is basically a plot of the current versus the voltage from a device or through a device. So it's basically here. We have the current, we have the voltage, and we go into the lab and we may measure a bunch of points. So maybe we measure some points here, and so the IV curve may be a line. We may measure some points here. It may be something like this. Depends on exactly what we're measuring. We can start with a very simple example for something for an IV curve. So we'll clear this out here. Let's just take a variable voltage source and some resistor R. And we're going to adjust the voltage on this source. We're going to tune it from various values. And we're going to measure the current I that is going through that resistor R. We already know the answer to this. It's Ohm's laws. The voltage is the current times the resistance, or since we're plotting current on that axis, the current is simply the voltage divided by the resistance. So if we have 0 voltage, we expect 0 current. Let's assume now we have a 1 kilo ohm resistor. So 1 kilo ohm resistor, if we put 1 volt, so here's 1 volt, 1 kilo ohm, we're going to get 1 milliamp. So we'll get a point here. 2 volts, 2 milliamps, and so forth. So we get an IV curve that looks something like that for a resistor, where the slope is 1 over the resistance of the thing. So that's basically the current flowing through some object. So that's one particular IV curve. So another thing we can do an IV curve for is some object that's providing voltage and current. And we usually refer to this as some sort of black box with 2 output leads. And we're interested in the current and voltage characteristics coming out of those leads. The way we'll do that is we will essentially measure the voltage across those leads and the current flowing through those leads, and we'll do that by putting various resistors in here that we can control. So there's a couple of obvious points on something like this. So what we're going to do is we're going to put various resistors across here. We'll measure the voltage and the current, and we could imagine initially not putting anything there. And then there's some voltage across these leads that the Vox puts out, so there's some open circuit voltage. Let's call it VOC. And there's no current flowing. So that is some point down here on this curve. We have VOC and no current flowing. So we have 0 current flowing. The next thing we could do is we could put a wire here and short circuit this. That's generally not very smart in the lab because we're likely to blow something up. But at least on the whiteboard here, we're unlikely to blow the whiteboard up. So we will just put a wire across there. That causes the voltage to go to 0. So the voltage equals 0, and we get some large circuit. We get a short circuit current, I short circuit. So we get another point on here. We have 0 volts and some current here, I short circuit. To measure the points between here, we'd have to put various resistors in here, some resistor, and then measure the voltage and the current, and that would give us a set of points. For a lot of the things that we do in this class, these are linear. So we'd measure a set of points that would fall on the line that goes between those. So if we put various resistors in, we'd measure various points here, and we get a line that looks like that. So the IV curve of some object that can deliver voltage and current may look something like this. It doesn't have to be linear, it could be nonlinear as well, but that's sort of the basic thing. So that's the idea of an IV curve. It characterizes either a component, the resistor like we talked about, or the output of some device. The next thing we want to talk about is the idea of an equivalent circuit. And when we say we have an equivalent circuit, we mean that the IV curve for the original circuit and the equivalent circuit are the same. So If we have two resistors in series, we know the same resistance is the sum of those. So the two resistors in series and the single resistor would have the same IV curve. Similarly, we could have circuits that would have the same IV curve as this that might be simpler than whatever is hidden inside of that black box. And that's what we're going to talk about next. So when we're talking about equivalent circuits, there's two special circuits that are important. One of them is a voltage source, or an ideal voltage source. And an ideal voltage source delivers the same voltage no matter what the current is. So if we do I and V, there's some voltage from the source, and the curve is just a line there. The voltage doesn't depend on the current. It's always the same voltage. You can guess what the other one is. It's a current source, and it delivers some same current independent of the voltage. And these have symbols, so this one is simply a battery symbol there, and this one is a symbol here with that current source. These two things are very, very useful. In fact, they don't exactly exist in nature. A battery is pretty close to this, and we'll see later in the semester that we can make something close to a perfect current source using transistors, but we can idealize those right now. And using a perfect voltage source and a perfect current source, we're able to define two sort of basic equivalent circuits that we use throughout this course and can show that are equivalent to everything. So we'll talk about those two circuits right now. The one with the voltage source is known as a Thevenin circuit. It's got a voltage which we call Thevenin, TH, and it has a resistor in series, R Thevenin, and it has two output leads there. So it's an ideal voltage source, a resistor in series with that, and we measure things there. So that would be our black box. The current source is something called a Norton current source, so it's a I Norton, and there's a Norton resistance in parallel with that, and the output goes there. So we have something that looks like this. So these are the two ideal circuits that these two circuits we have that are equivalent to just about everything we do in this course. Let's now talk about the IV curves a little bit here. So here is I and V. We can start by doing the same thing we did last time. We can not connect anything here, and then there's going to be no current, but we're going to get V Thevenin. And we can short circuit it. We can connect these together, and then the current that's going to flow is going to be this voltage divided by that resistance. So we're going to have a current V Thevenin divided by R Thevenin, and what connects in between is something that looks like this, and the slope is minus 1 over R Thevenin there. So that's the IV curve of this, the IV curve of this circuit. Let's start with the short circuit. We connect a wire here. All the current's going to flow through the wire, and that has to be I Norton. So we're going to get I Norton there. If we leave this completely open, so there's nothing there, then we have this current flowing through that resistor. The voltage drop is I Norton times R Norton, so we have I Norton times R Norton for the voltage, and it connects up like this here, and the slope is minus 1 over R Norton. So these are the two equivalent circuits. Those two circuits would be exactly equivalent to each other if we did one thing. If we set I Norton equal to V Thevenin over R Thevenin, and I Norton times R Norton equal to V Thevenin. Let's do that here. Let's set I Norton equals V Thevenin over R Thevenin, and V Thevenin equals I Norton times R Norton. That's true if R Thevenin equals R Norton. So if R Thevenin is R Norton, then the Norton current is the Thevenin resistance voltage divided by the resistance, and the Thevenin voltage is the Norton current times R Thevenin. So those two are equivalent under that assumption there. The one that's going to be useful for us, particularly useful for us in this course, is the Thevenin equivalent, because that one is something we will equate a lot of things to. So that's the one we will look at a lot as we go through this course. But here we have Thevenin equivalent, Norton equivalent, same IV curves under some basic assumptions about this, which means that they're equivalent. And what we'll show is that a lot of the circuits that we have in this course can either exactly map onto these or can approximately map onto these in certain regions very, very well. So we can characterize them by this very simple circuit, which is just a voltage source and a resistor. And we don't have to worry about more complicated things inside.